All right, gang. So, this is the second Cisco module, and this one is all about routing and switching. It's an introduction to switch networks. And you talk about switch networks, a little bit in the first one, but in this one, we're going to actually get into what switching is and why it's important. And specifically, we'll talk about what switching has done as far as making networks faster. Now, a lot of people start this one and say, is there really that much to talk about switching? And it sounds like no, because for most small networks, thinking about, our lab up at Bipsy or the lab that I have out at Barksdale, those small networks, there's not a lot to switching on those. But switching can do a lot more than just what we tend to think of. In fact, if I were to ask you, most of you probably have wireless at home, and chances are great that your wireless network has got a little switch built into it. And the switches, the thing that's important about them is that they only send traffic out the port that it needs to go out. What they do, if you think back to the first Cisco module, is they shrink these collision domains, which is the chances of two machines on a network talking at the same time. And by shrinking those domains, you're able to transmit more data because a collision makes the whole network stop to try to figure out what happened. So in this one, we'll talk about LAN design. We'll talk about the switched environment. After we finish this chapter, you'll understand convergence, which is something that we've not talked a lot about, but convergence is kind of important in a network. And I don't want to get ahead of myself since one of these slides talks about it. We'll talk about switch networks in medium to small businesses, which, chances are, as most of you finish this program and go out and get a job, especially if you're going to stay around the Shreveport area, you're going to work for a small to a medium-sized business. Most of them are going to have switches, but they're not going to be super large networks. And switching in a small network is a little different from a large network because there's less things normally that you have to deal with. We'll talk about what frame forwarding is, and then we'll talk about the differences in collision domains and broadcast domains. And when we get into that, I want y'all to pay very close attention because I know there's questions on the test about making sure you understand those. In fact, what the test will do is they'll draw you a network and they'll ask you how many collision domains are in the network and how many broadcast domains. And you have to look at it and figure out what are switches and what are hubs and what are routers to be able to know that. All right, so convergence is basically the idea that we no longer have networks where just one type of data exists on that network. What I mean is now, even in medium and small businesses, you're finding networks that people will use where they use voice and they use data and they may also have video all on one network. A good example of this is the Fios service or the UVerse service to the home. I'm actually on a Fios connection right now. And what Fios does is it provides a piece of fiber to your house, but on that fiber you have a telephone, you have a TV, and you have your internet as well. And all of that data, even though it's all different types of data, the way the Fios network looks at it is IP packets. It just transmits the data in packets and then breaks it up to send it to the different devices. An area that is very, very, very fastly growing right now in this is voice over IP. And that is basically using the internet for telephone service. One of the reasons that it has taken off is because the telephone system still in so many areas wants to charge per minute for long distance. A good example is my mom's house. My mom lives out in Spring Hill in the middle of nowhere. And Shreveport actually on a standard old telephone line is long distance from Spring Hill. So under her normal phone plan, when she just had a CenturyTel telephone up there, she had to pay a long distance rate. I mean, now granted, it was cheap. It's like 6 cents a minute or something. But she'd have to pay that every time she called me. So I moved her over to a voice over IP system, and she was able to keep her phone number. But now, for I think it's like $9 a month if you pay for it for a year, she gets unlimited local and long distance and all that. And the reason VoIP is so much cheaper is it transmits this data over the internet till it gets into an area where you're actually trying to make the call. And then it'll go through a gateway, a VoIP gateway. But that gateway uses the normal phone system as a local number instead of a long distance number. So it cuts a lot out of it. Um, Another thing that is important about the complexity of networks is that nowadays, more than ever, more and more people are working from home, and they are road warriors. They're accessing networks from hotels. So we've seen an increase in the need to have remote access to data. You know, if you think back, say, 10 years ago, that was something that was fairly unheard of outside of the real big tech sectors. You didn't have a lot of people that were wanting to access that data remotely. But now it's pretty common for people to check into a hotel and get on the hotel's free Wi-Fi and need access to their corporate data. And there's a whole nother section on security of that, which becomes somewhat of a nightmare because as a net admin, when you need to provide this access, you've got to learn how to secure a network that doesn't actually belong to you. So that's where you start using things like encryption and all between the laptop and your connection because you don't control anything in the middle. Another thing is because we do so much on computer networks now, we need them to be way more reliable and available than was needed previously. In the old days, it was, you know, if a net admin needed to do some maintenance, pretty much all he would do is send an email around and say, hey, on Friday at 3 o'clock, I'm going to shut down the network for 30 minutes. So everybody make sure you back up your data and shut down your computer before 3 o'clock. Even just when I was at the juvenile court, which wasn't that long ago now, that was something I would do. I'd send them all an email and say, hey, there's not court this afternoon. I need to back up this database. So at 3 o'clock, y'all get out or I'm going to boot you out. But now with convergence, you have more things that are kind of more mission critical than just data. What I mean by that is phone systems, for example. If you're using a VoIP phone system, you need to keep that thing up pretty much all the time. If you're a business like, say, a call center, that becomes an absolute mission critical thing for you. Because if you're a call center and people call to pay their Comcast bill or whatever and get a busy signal, Comcast is going to get mad at you and, you know, you're not going to be able to provide that service. So you're probably going to break your contract. And that's another place you're going to see that switching comes in, is that we can add redundancy to networks by making multiple pathways for things. So some of the elements about a converged network. Collaboration is a requirement. Here in this little diagram, they're showing us a picture of a VoIP phone. We've got a little bit of email and a webcam. And you see that they're drawing this so that they all go into one funnel. And each of these are IP services. So as IP services, they're just treated as data on the network. It wouldn't matter really what kind of data as long as it's treated that way. Now, the three examples that I tend to use most often when we talk about converged networks are video, you know, data and voice. But there can be others. Basically, any kind of data that can be converted into an IP stream can be put on one of these types of networks. The only other type that really comes to mind is if by chance any of you work in an industrial setting, there is something called a PLC. And basically PLCs are controls that actually physically control things out in a plant. There are tons of different ones, but the most common PLC that I can come up with is if you're in like an oil refinery. Most of the valves in oil refineries now are no longer, hey, call somebody on the radio and tell them to run out and close this valve or open this valve. PLCs allow that to happen on the network. So the engineer can be sitting at his computer and say, I need to close valve 1704, and he can issue a command and shut that down. Well, with convergence, that all can be sent on a standard network that's already run through a plant. An issue with that comes into play with security. You know, you want to maybe as the engineer be able to do that, but you need no one else to do that. Other things they talk about: call control, voice messaging, mobility, and automated attendant are also some features. One thing about VoIP is because it's data, it doesn't really matter where it's connected. There are things called soft phones that is basically software you load onto your computer, and with that software you are able to have a phone. It's just not a physical device, it's through your actual computer. But if you are a road warrior and you work, you know, out of a hotel a lot of the times, with this, you can actually receive and send calls when you're logged in, and they'll go to your normal number, like your office number. I'm a big fan of Google Voice, for example. The number that's on my syllabus for all of you is actually a Google Voice number. And that number is actually not assigned to any phone anywhere. It's on my computer. But if one of you calls me and leaves a message on it, I can turn around and call you back from my computer, and I'm dialing it like a local number to call you, and you guys are dialing a local number to get me. The other cool thing about Google Voice, y'all should all kind of check it out if you get a little bit of time. It's absolutely free. So you can go to google.com/voice and get yourself one if you want to play around with it. And you can forward it to any number you desire once you authorize that you have access to that number. The way you authorize it on the Google Voice system is they call you at that number and then tell you to enter a 4-digit code. So I have you call my Google Voice number, but I can have that forwarded to a number over here in Dallas where I am right now, or to my cell phone, or to my office, or to Barksdale, which is the real reason I did that. So if somebody actually calls me during office hours, I can forward it to whatever phone number I happen to be at that time. So the benefits of a converged network, I really kind of have already talked about this. Multiple types of traffic, only one network to manage. Substantial savings over the installation and management of separate networks. Because we're dealing with one network, it is a whole lot cheaper and easier to do. In the old days, with medium and large businesses, it was pretty common to have what's called a PBX to deal with their phone systems. And the PBX ran basically like a phone network, if you will. But you had to run your own wires for that. You had your own phone switches. You had your own phone equipment that was needed to run all of this. Then on top of that, you had your data network. So if an office had a phone line and a data line, you had to run 2 sets of wires and put 2 different jacks in and set up 2 different types of equipment, all to run this one thing. Then on top of that, let's say it's a place that uses video. Maybe they've got a closed circuit TV to ensure the security of the building. We had to run separate coax wire for all of that. And if it was a really big system, there were switches that would run into. And that would then run to some sort of recorder that was recording everything. Then somebody would have to go back and look at it, and all these things. With convergence, all of that is treated as data. And once everything is treated as a single type of data, it becomes so much easier to manage. We'll move forward here. I'm getting a little ahead of myself, but we talk about what's called QoS, or quality of service. And that really comes into play with these converged networks because you can give certain types of data priority over others. For example, if I'm a call center, I may put VoIP at the very top of the list and email at the bottom because I think it's more important that my phone calls come in than my email. Even though the emails will still come in, they'll just be a little slower. I'm giving priority to what types of traffic I want to. So Cisco calls these networks borderless switch networks. And a borderless network is a network architecture that allows organizations to connect anyone, anywhere, anytime, and use these devices securely. This is designed to handle some of the business's challenges, such as converged networks. So basically, this is just getting into Cisco's terminology, and they call all of this convergent a borderless network. And what they mean by that, you'll see when we go forward and start talking about VPNs a little bit, that because everything is borderless, meaning it's all one type of data, that can be put through any type of pipe that is needed. If you use Cisco VPN and dial in on the internet through an encrypted connection, all of that data, as long as it's in, you have a fast enough pipe to handle it, can come out the other end on your computer to be voice or to be data or to be video, whatever it's needed. So here is just the hierarchy of a borderless switch network. And this is just the way they break up the network to explain it. In the three-tier design, you have the core network, distribution network, and then access. And access is the layer where we're actually going out to the individual computers. You notice the symbol they put here on access is actually the symbol for a switch. Under a two-tier design, the core and the distribution are linked together. And then that is linked out to access that goes to the individual users. Really, the big differences in these are sizes of networks. The two-tier design is kind of used for smaller and medium networks because you're combining your core network with your distribution. And then in the three-tier design, you've got just extra distribution spots. A good example of a three-tier might be a college campus where you have computing services that's going to have a core. And then you might have distribution that's each building, and then access that's each floor of a building, and those switches on each floor of the building go out to actually the individual computers. So here's just another example showing core, distribution, and access. They show building A as management. It's funny that they're using these names. They could have put G there and we'd have said what we actually have at BIPSI because all of computing services is in the corner of building G. But you see the core goes to a distribution node in each building, and then access would be each floor of those buildings. So the role of switching is that switching is kind of crucial to network design. It allows the traffic to be sent only where it's needed in most cases, and that's important. We'll talk about why later. A switch LAN allows more flexibility, more traffic management, and it supports things we were talking about earlier, QoS or quality of service, additional security, wireless, IP telephony, and mobility services. So here are just some examples of the different types of switches that specifically Cisco has, which is what we'll talk about here. And this is the fixed platform form factor. These are the ones that you're probably most familiar with. And what a fixed platform means is that these are designed where you've got the number of ports they come with. You buy a 48 port fixed platform switch and it's got 48 ports on it. That's all there is. Now, I don't really like this term. It's a little bit of a misnomer because some of what are considered fixed platform actually have a place where you can update one particular port to be a different type of media than the rest. And that's done with what used to be called a GBIC. It has a new name now. But basically, it's a little device that slides into one little port on the corner of these devices. And the reason for it is that it's not uncommon in a big building for you to have a piece of fiber that runs from the top of the building to the bottom, but you need actual ports on each of the floors. So you would run the fiber between the switches, but then the copper itself will run out to the connections on those floors. And that one port is just to connect two other switches. Then at the bottom, you would your final fiber port would connect probably to some sort of distribution that would be like a ring going around a campus or something. Now, modular are the ones that you may not be as familiar with, but a modular one are for some of your larger switches. And I'll try to find a couple of pictures of these. I don't actually have anything in our labs that is modular anymore. But Computing Services does have a few of these. The big difference is they are HP instead of Cisco. But modular platform is exactly as it sounds. With a modular platform system, you are able to change the cards out to put different types of ports in the system as you're going. And the reason for that is that you may need some that are fiber and some that are copper. Maybe you want to put a firewall module in it. These are mainly used in distribution points because they accept different types of connections. In fact, the network over at LSUS is one that I am very familiar with. And over there, there's a core HP. I believe it's a 5909, but I don't remember the number. But it's one of these large switches that has different ports. And that particular one that we have over there has 9 slots, 9 of these cards. Each of these are large cards if you see them. It has spots for 9 of those. And we have over there 2 that have 48 port gigabit switches in them. And that actually covers all of the admin building at LSUS. So that actually runs to all the actual computers. Then we've also got 2 firewall modules, and then we've got a proxy module. And the proxy is what we run everything through at BIPSI, at LSU to make sure that no one is going to any websites they shouldn't or anything like that. Then finally, we've got 2 more connection slots that are connections for our ISP connection. And one is a fiber that runs on a network called LANI, which is the Louisiana Optical Network. And the other one has a DSL modem in it. And the backup link over there is just a standard commodity DSL network like you could buy for your house, which when we're switched onto it over there, it's very, very slow, but it's still network connectivity. It still allows a connection. And the reason we chose DSL over there over cable is because the fiber connection for LANI runs into the front of the campus, but the phone system DSL runs out of the back of the campus. The cable also runs in the front. But if someone is to cut that pipe with cable and with our fiber in it, we would lose connectivity altogether. We'd lose cable as well. But since the phone lines run out the back of the campus, the chances of somebody cutting both of those at the same time is very low. So that still allows us to have connectivity even if it's very slow. Now, the reason these things, instead of having individual devices, you want this is for manageability. If you have everything in one box, it's easier to manage. Most of these also have redundancy on the back of them, such as they've got extra power supplies and things like that. So this is the stackable platform. And these normally you stack with the GBICs that I talked about earlier, but with stackable platform routers, you actually can connect them in the back with a special cable, and when they're connected, they act as one switch. I'm honestly not certain if Cisco still makes a lot of these. These were very common, and the reason you had that special port is because it was much faster than just a regular connection. You can stack switches by connecting one port, like port 24 on the front of one, to port 1 on the one above it. But then they act as separate switches. When you connect them together on the back like this, they have one management IP address and act as one switch. So if we were to log into the switch they show here, not knowing the numbers, but if I assumed that each of those was a 12-port switch, then you see I would have a total of 48 ports, and just one IP would manage them all. So when we deal with switches, what we're actually dealing with is called a frame forwarding. And a switch makes a decision based on where the data comes in and a destination port. The switch keeps a table that is used to determine how it's going to forward traffic through the switch. Cisco LAN switches forward Ethernet frames based on the destination MAC address of the frame. Now think back to your Cisco 1 and even before that, your Network Plus days. A MAC address is a physical address. Every network card has got a MAC address, and that MAC address is going to have data about the computer on it. And it's when you translate IP into MAC, what you're going to get is a MAC destination and a MAC source. Well, switches look at specifically the MAC addresses. And the reason that's important is that we talk about just IP really as being the data that everything is these days. And I don't know the numbers, but I bet it's 99.999% of data out there now is just IP. But because we're working with MAC addresses when we're forwarding with switches, we don't have to use IP. If we were to build a lab full of old Mac computers and we were using the AppleTalk protocol, AppleTalk still uses Ethernet, so AppleTalk data, once it's encapsulated, still has a frame that has a source and a destination MAC. That means that data can be forwarded through one of these switches just like any other type of data. In fact, you can have networks that have both of those on it. Again, it's not common anymore because everything tends to be IP, but I could have a lab that had 10 Macs and 10 PCs in it, and because it's Ethernet frames, one switch will send the data to the right ports no matter what. So a switch has to learn what ports are in use and what devices are on those ports before it can transmit a frame. And it does that by building this table of MAC addresses to what addresses are on what port. And that is called a CAM table. CAM is a special type of memory that is used in switches for high-speed searching. One thing that we really don't talk about a lot here, but I'll just go into as a refresher for you guys. A switch is really just a small computer. This is just memory in this small computer that holds this table, but it holds it in such a way that it can look at it very quickly, because the key to a fast network is being able to switch data very fast. So the information in the MAC address table is used to send the frames. When the switch receives an incoming frame from a MAC that is not found on the CAM table, it floods it to all ports but the one it was received on. So this is something that you can actually even see at home if you've got a switch on your wireless network, or if you've got a switch plugged into anything. If you unplug that switch and plug it back in and then send data immediately, as soon as you plug it back in, that data for just one or two pieces of, one or two frames will go to every port on your switch. And the reason for that is because it's sending that data on, it doesn't really know where to send it. On a larger network, it takes a little bit longer. Once you plug in a switch and, if you've turned it off and back on or whatever, that data, it'll take it just, a few seconds or a little bit longer to determine what ports are on what, or what MAC addresses are on what ports. So by that, it has to know where to send data. And the backup is, if it doesn't know where to send it to everyone, because that ensures that that data will be delivered, even though it means all of the ports will see the data. So there are different types of forwarding. And I see here that CISCO has left us a little add a header there, unless they're talking about the header on the actual port frame. But anyways, so two methods of forwarding data: store and forward, and cut through. Now, each one has its own pluses and minuses, and I believe that future slides talk about them, so I'm not going to go into it in detail here. But store and forward basically gets the entire frame first and computes what's called a cyclic redundancy check. And if you think back to some of your other classes, a CRC is just a mathematical algorithm that we're going to run on that data, and it's going to provide a number. The reason we run that number is because that number is stored in the packet of data coming from another system. So we run it and then see that the number we get is the same as the number that's in the data. If it's the same as the number that's already in the data, then we can assume it's valid because the two numbers match up. And the probability of two pieces matching up that don't contain the same data is very, very, very low. So once we've computed that, we assume it's a good frame and we forward it to the correct port. Now, cut through is a little different. Cut through sends the data on as soon as it gets the destination MAC address, which means it sends the data on through before it even has the whole frame. Now, the plus to cut through is speed. Cut through is faster than store and forward. The minus, however, is that cut through can send bad data, because if it receives a bad packet, but the destination address, the first part of the frame was okay, the destination and the source, it's going to send it on. It doesn't care that it's good or bad, because it's not going to compute this CRC on it to determine that it's good or bad. So store and forward allows us to check for errors and perform automatic buffering, but it's slower. Here's an example of a store and forward. We're just looking more at what we were just talking about. Here's a header, a typical header. We've got an 8-byte preamble. Then the destination MAC address is the next 6 bytes. So we know that data here. This is where I'm going to jump ahead and kind of compare this to cut through, because see, as soon as we got the first bit of this frame header, we could send it on and cut through. But you notice that the FCS checksum, our cyclic redundancy check, is at the very end. Why is it at the end? You need the whole packet to compute it anyways. So store and forward needs to get this whole packet before it does anything. And here they show if we're using jumbo frames, which I'll get into later. We talked about them in the first one, but we'll hit them again, I'm pretty sure. I need the whole frame. I need all the bytes before I can make a forwarding decision, because I need to compute that CRC to make sure the data is valid. Now here we'll compare that. Cut through allows the switch to start forwarding in about 10 microseconds. It's very quick. There is no redundancy check, however, and there's no automatic buffering. And here we're seeing an example of that. You notice we can forward as soon as we get the destination MAC address. So, 14 bytes into a frame, and we're ready to send it on. So now something we've got to make sure that we understand are switching domains and collision domains. And a collision domain is where the segment where devices must compete to communicate. This is where hubs, if you happen to run into hubs, come into play. All ports on a hub belong to the same collision domain. Every port on a switch, however, is a collision domain of its own. A switch breaks the segment into smaller collision domains, easing device competition. The reason that hubs exist at all is because in the old days, when computers were very expensive and switches were very expensive because memory was expensive, a hub was significantly cheaper than a switch. So what was pretty common in old days was to set up, like if we're thinking about a college campus again, each of the labs may have hubs that connect all the ports in that lab. And then one port on that hub would go to a switch, and the switch would connect 2 or 3 labs together. Then your switch would connect to whatever you had running between the buildings to get you on the main network or the internet or whatever. So again, remember that a hub, all the ports on a hub are in a single collision domain, but every port on a switch is in a collision domain of its own. I totally expect you guys to see diagrams on your CISCO exam where they ask you how many collision domains are in this picture. And they're going to show you a switch with 2 or 3 ports, and I'm almost certain there'll be a hub thrown in there, 1 or 2 hubs to make you figure out the collision domains. Now, broadcast domains are a little different. A broadcast domain is the extent of the network where a broadcast frame can be heard. Now, think back to CISCO 1. Remember that a broadcast frame is just going to have a destination of all Fs. So in hexadecimal all Fs, we know that that's a broadcast, and that's going to go to every port no matter what. But a broadcast domain breaks where those are sent, and that's done with a router. Switches will forward broadcast frames to all ports, so they don't break it. All ports of a switch with its default configuration belong to the same broadcast domain. The reason it becomes important that you notice this default config here is because when we start dealing with VLANs or virtual LANs, then we can break different ports into different broadcast domains, but our switch has to act like a router to connect those two together. If two or more switches are connected, broadcasts are forwarded to all ports of all switches, except for the port that originally received the broadcast. So switches help alleviate network congestion. And they do this by facilitating the segmentation of a LAN into separate collision domains, providing full duplex communication between the devices. They take advantage of their high port density. They buffer large frames. They have high-speed ports, and they have a low per port cost. If by some chance you're dealing with an old network, you go in somewhere and they hire you as an admin or as a consultant, and you see that they still have hubs, one thing you can do immediately and pretty cheap is take out those hubs and put in switches. And you will see a very, very immediate, faster network than what those hubs are going to provide. In fact, occasionally I ask my advanced networking class a question about the only places that hubs are really useful anymore. And I'll tell you guys this. This is an aside. The only place that I ever use a hub for anything anymore is if you're dealing with an unmanaged switch and you have a device on it that you need to capture data from. Because a switch only sends data to the port that it should go to, not to all the ports, it's almost impossible to monitor a port on a switch. I'm using the word unmanaged here, and the reason is if it's a managed switch, I can go on and change the configuration and say everything that goes to port 5, I want to go to port 6 as well. So that gives me a way to check it. So I would have to plug my switch into the hub and then run each of two ports on the hub, one to a monitoring system where I'm going to run something like Wireshark, and then one I would have going to the actual device I'm trying to monitor. So, all right, in this chapter we talked about that the trend in networks is convergence, which again is just the combining of all that data onto one network. There has been a dramatic shift in the way businesses operate because of this. If we deal with Cisco borderless networks, the whole idea is that it doesn't matter where the data is coming from or where it's going to. It's treated as a single network. We talked about the three-layer hierarchical design to divide up a network. We talked about switches, specifically switches used store and forward or cut through. Make sure you understand the differences on those. And when you get into chapter 1 on the actual CISCO module, you'll see that there's going to be a few questions on them. Make sure you understand them. Every port on a switch forms a separate collision domain, allowing for high-speed, full duplex communication. Switch ports do not block broadcasts by default, however. So that is a rundown of Chapter 1.